everything is settled. We lost 20 minutes, but anyhow. Yeah, and any question?
Sir, the degenerate eigenstate we choose here,
Hmm.
uh, are they complete? Complete set?
No, no. Complete set means complete set when you talk about that full spectrum, no? When you try to calculate the perturbative correction EN1 first order correction to the nth level, so we are considering that a level perturbation correction we want to find, that level is twofold degenerate. We are not talking about the whole spectrum. Complete set means it will come when we consider whole spectrum. We are focusing, did you get my point? We are focusing to a particular state, and that particular state is degenerate. And what will be the correction to that state? We are not looking at the whole spectrum. So no question of completeness here.
Sir, my second question is, while we considering the perturbation
Huh.
of that set, we are particular to those two degenerate state or all the eigenstates in the set?
No,
Because
no, we are
we,
no, no. Say again your question.
sir, we are considering the perturbation for those two degenerate state or all these eigenstates.
Those two degenerate state. We are focusing only on a particular state, and that state is degenerate. So this is focusing on a particular state.
Sir, what about other?
Yeah, you can take any state. Suppose I am
For other
focusing,
state,
but it
sir,
is
for other
arbitrary. No, 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 no. You are not understanding at all. When you calculate, when you calculate the correction, first order correction, it is the nth level, right? When you calculate the wave function correction, it is the nth level. N can be ground state, N can be first excited, N can be second excited, N can be third excited. So in principle, you can calculate the correction to any state, and each state you have to do separately. You cannot find a theory where you can find that all the state, but it is arbitrary state. Now, in case of degenerate case, I am assuming the nth state of the system is twofold degenerate. This twofold, I am assuming. It can be threefold, it can be fourfold, it can be n-fold, it can be anything. But I am giving the idea for twofold. Now we can generalize to threefold. Is that clear or not?
so we are considering only nth state, nth degenerate
Yeah,
state.
nth state which is degenerate. That
For
nth state also we consider non-degenerate perturbation theory. Yes. Now tell me.
uh, sir, sir, for other state we can use non-degenerate state perturbation theory.
No, if they are degenerate, you have to use degenerate. If they are non-degenerate, you can use non-degenerate. Other
Yes,
state
sir, that's
depending
my
on the other state whether they are degenerate or not, that you have to first find. First you look at nth state, any nth state. What is the degeneracy? If there is no degeneracy, apply the non-degenerate perturbation theory. If there is a degeneracy, then apply the degenerate perturbation theory. Okay, I forgot to tell you that there is recording facility in BHU site is not available. So I cannot record the meeting. Anybody wants to record it, please record and send it to me. This Pokhar last time could not record full correctly because audio was not there. So I request somebody, at least 2-3 people can record, and who can record clearly, I'll put it in the YouTube. Otherwise, I'll not be able to put in the YouTube because recording facility has been withdrawn from BHU. I am asking the authority to reload, but since that facility is not available, I cannot record. Yeah, so please somebody should record if you need recorded lecture.
Sir,
Huh.
sir, you said that perturbation breaks the degeneracy, but I don't understand what is the meaning of this. Can you repeat it?
Breaking of degeneracy meaning what? This is, tell me. Breaking of degeneracy means that before perturbation your state were degenerate. After perturbation your state are not degenerate. So this is the meaning of breaking. Now it is clear or not?
हाँ मतलब कैसे डिजेनरेसी ब्रेक हो रहा है ये समझ में नहीं आ रहा.
That I said, no? So you suppose you not listening up, look. Na has a degenerate n with energy E n0, okay, and nb you had the energy zeroth order, all zeroth order had the energy E n0. So that means two state have the same energy. That means they are degenerate. Okay. So after perturbation, this is for H0. Now, if you have a H prime, if you have a H prime, if you perturbation, when perturbation is applied, then we find that there is a correction, and that correction is En. There are two correction. It is 2 cross 2 matrix, so there will be two eigenvalues. So suppose those eigenvalues are A and B, capital A and B. So N0 will be A1 state, N sorry E A E sorry En. Let me write clearly. En, this is the energy plus A. Now this and this En0 plus B. Earlier you had energy En0, En0 both. This is degenerate. Now after perturbation you have energy. In one case it is added A, another case it is added B. Are they equal? If A or B are different, are they equal? Answer me.
No sir, no sir.
They are not equal. So they are not non-degenerate. So this is breaking.
Okay,
Here,
sir, okay.
here it was degenerate. Here we have, when you have correction, it is different energy level. So it is breaking degeneracy.
Sir?
Huh.
Sir, for n number of eigenstate, there is corresponding n number of eigenvalues, and suppose there.
No. Just you have a system, quantum system, where you said n number of eigenstate.
Yes, sir.
N, for me, n is any arbitrary value. N can be 0, n can be 1, n can be 2. But you are saying n number of infinite number of.
N number of arbitrary
So that you
eigenstates.
so you represent that by capital N. Capital is the
Yes,
total number. This n is
total
too
number.
arbitrary. Huh. Now tell
Then
me your.
they corresponding to them, there are also n number of eigenvalues.
May or may not be, right?
That I'm saying. My point is, among those n number of states, there may be only two eigenstates exist which are degenerate, corresponding to same eigenvalue.
Yeah.
In that case, what we can do? We can apply only degenerate degenerate perturbation theory for those particular two states, and for rest we are apply non-degenerate state, non-degenerate perturbation theory.
Yeah.
Like that.
Yeah. That I'm saying repeatedly. I don't know why you people are not able to follow that. I can suppose a box problem. Suppose harmonic oscillator problem. En equal to n plus half h cut omega. It is always non-degenerate for any value of n. So you will apply the non-degenerate perturbation theory. Now hydrogen atom. Suppose hydrogen atom is three-dimensional, its energy levels are given minus 13.6 by n square, and wave function are given NLM. So for so this n equal to 1, what are the wave function? Wave function will be psi 1, L value can be 0, M value 0, only possibilities. N equal to 2, psi 200, psi 211, psi 210, psi 21 minus 1, 4 eigen function. What is the energy? All 4 eigen function has energy minus 13.6 by 4. This has energy minus 13.6. So this state is non-degenerate. One state, one energy. This state, 4 state, one energy. So 4-fold degenerate. Okay. So when I apply perturbation theory, if I ask to find the what is the correction to ground state, then I will use non-degenerate perturbation. If I ask to find the correction to the second state, first excited state or n equal to 2 state, then I will use degenerate perturbation theory. Is that clear now?
Yes, sir.
Anybody has any other question? It should be clear to you. Yeah, last lecture, of course, I of course could not upload because I could not record. So maybe that is why you may have question. But it is good that if you can bring more question. Anybody has any doubt? So today, what we'll do, we'll consider we'll consider that we'll consider an example in hydrogen atom, particularly this example. This is famous example. Everybody learns this example, that when you apply a electric field, that will create a weak electric field, that will be a perturbation. Then what will happen to this energy level and this eigenfunction? So that we are now going to discuss. But before that, one important result I'll mention, that if you have a operator A, suppose, or let me write O. If you have an operator and if it commutes with your H0 and also your H prime, perturbative Hamiltonian and the unperturbed Hamiltonian both. Suppose if you has commute, then what I'm going to say is that even if you have a degeneracy, you can use non-degenerate perturbation, non-degenerate perturbation theory. This is an important result. I'm going to prove it. Suppose if I find an operator that commutes with your H0 and it also commutes with your H prime, then you can use non-degenerate perturbation theory even for the degenerate case. The statement is clear to you? I forgot my notes also today, so let me check my old notes in computer just for a minute. So I'll first, let me tell, please read this statement, and if you have any question, tell me that you have understood this question or not. This simple proof, I think it can be in Arshankar or maybe in Griffith, I don't remember, but I think Arshankar. So this proof you can read from there also, but I'll prove it. Online lecture 103. Lecture 14, let us see, 14, 13, what is that? Okay, so just a moment, I'll try to find my lecture, online lectures, it is there. Perturbation theory I have started here, okay. Okay, good, good. And then we'll consider this hydrogen atom problem that
Sir, O can be any operator
uh,
or specific? O
O,
can be any operator or specific operator.
any operator which commutes with this. O's character of O has to be that it has to commute with H0 and also commute with H prime. Any operator. But this is a strong restriction. No? It has to commute with H0 and also has to commute with H prime. Then only.
It is the main condition. It is the main
It,
condition
it is a
only.
condition. If you can find a operator, any operator, which commutes with these two, then I'll show you that degenerate perturbation theory is not needed. You can do only non-degenerate, which is easier to do. Okay. And of course the operator has to be Hermitian. Hermitian. In quantum mechanics, we don't talk about non-Hermitian operators, that self-adjoint or Hermitian that I told you. So it has to be Hermitian, of course. Okay, so I got this proof. Okay, so now let us prove this. So H0 and A has commutator equal to 0. And we have H0 and suppose your state, that state, nth state is degenerate. You have Na0 and Nb0 two state corresponding to energy Na0. Suppose this twofold degenerate. So H0 in A0 is a eigenstate of H0. Na0 should give you En0 of Na0. But A is, sorry, not A, O. Sorry, O. I'm using O. So O is commuting with H0. So it can be that O of Na0 will be some other eigenvalue, say mu, or let me alpha times Na0. Similarly, O acting on NB0 state, it can give you a beta NB0 state. Why I can do that? Because it is commuting with this. So when it commutes, it must have simultaneous eigenfunction. So Na0 is simultaneously eigenfunction of H0 and also O. And I am assuming this they should have a different distinct eigenvalues, otherwise they will be same state, right? So there one case A state we have alpha, another case we have beta, or you may write alpha A and alpha B. Okay, so that will be more convenient too. Okay, now let us consider now let us consider that this O operator also commutes with the H prime. So if I calculate this and then expectation value of this quantity between say Na0 H prime commutator times O times Nb0, that should be 0 because this operator itself 0. So if I take a inner product in this, it will be 0. Okay. Now let us calculate this. What will happen? So Na0 times H prime O minus O times H prime Nb0. Okay. So this is the meaning of the commutator, and that should be 0. Now Na0 H prime O times Nb0 minus Na0 O H prime Nb0. Okay. Just now this acts on this will give you a alpha A, O acting on Nb state giving you alpha B. So I can write this state is alpha B, then H prime AB. because remember the notation, H prime AB is just NA 0, H prime NB 0. Okay. So A and B, so NB, and this side, this is left, so it cannot act on NB. So it is, but it is a Hermitian operator. That is why I said a Hermitian. So it can act on, of course, it is in the Kate space, but it can act on the Brass space. Okay, so it will give you a alpha A times again H prime AB, and this quantity is 0 on the right hand side. So this I can take common. So alpha B minus alpha A times H prime AB equal to 0. So implies alpha A and alpha B are different, that I told you in the beginning, that they are different, otherwise no meaning, their state will be same. Okay, so this cannot be 0, so it implies HAB should be 0. So this because alpha B is not equal to alpha A, this already know. So H prime, now look at this matrix. We had the matrix HAA, H prime AB, H prime BA, and H prime BB. So this matrix eigenvalues are the corrections. But now I found that HBA equal to 0. So now this matrix under this condition will reduce to H prime AA 0, H prime say BA, and H prime BB. Now its eigenvalues, so if you diagonalize this, H prime AA minus lambda times H prime BB minus lambda equal to 0, determinant. So lambda, the correction will be H prime AA, or correction will be, so one correction is H prime AA, another correction will be H prime BB. But what is the meaning of H prime AB? It is NA0 H prime NA, and it is NB0 H prime NB. So this is first order correction. This is the non-degenerate case, first order correction for non-degenerate. So this is the first order correction for non-degenerate case. Okay. Now if you have any question, it should be clear. And anybody has any doubts?
H prime B, sir, H prime B is not a 0.
It need not be
H prime
0.
B.
It can be 0. It need not be 0. Even if it is non-zero, generally HAB equal to 0. Generally BA also equal to 0, because it is complex conjugate. So generally it will be 0. But even if it is not 0, then also generally it is 0, right? For a Hermitian operator H prime, it is 0. But we are not bothering about that. If HAB is 0, then it is Hermitian. See, NA0 H prime NB0. If you take a Hermitian conjugate, if it is a Hermitian operator, it will be NB0 H prime Hermitian, so it will be same self-adjoint or Hermitian A star. So this is basically star of, so H prime BA equal to H prime AB star, right? So for a Hermitian H prime. So this when this is 0, this also will be 0 for Hermitian. Okay. So but it need not be. Even if it is not 0, then also you can have. So what is the result? Result is that if you can find, suppose I have a degenerate state, I have a quantum system, and one of the state is degenerate. Suppose this state is, first excited state is degenerate. Now, if I can construct a operator O which is commuting with H0 and also commuting with H prime. Suppose I immediately construct this, then I'll use non-degenerate perturbation theory. I'll not use degenerate perturbation theory. But this construction may not be easy. If it may be very easy, it may not be very easy. But in case you can construct, you can avoid non-degenerate, avoid degenerate perturbation theory and do non-degenerate perturbation theory. Okay. Now, one more thing I want to tell. So, in degenerate perturbation theory, what you do, you diagonalize 2 by 2 case, you diagonalize this matrix. BB. And the eigenvalues are correction. And eigenvector, suppose this is my NA0 state, this is my NB0 state, and this side, this is my N0 state, this is my NB0 state. Then only you can get this. So eigenvalues are the correction, and eigenvectors also we need. Suppose I get eigenvector like this, 1 over 2 in one case for 1, 1, and in another case I get 1 minus 1, say, suppose. Okay, then, so this corresponding to En, okay, this will correspond to, okay, so 2 eigenvalues, so this is correspond to first eigenvalue, this correspond to, or say A eigenvalue, this correspond to the second, which is say B eigenvalue. Okay, so I'll write En0A plus A, this state eigenvector will be 1 over root 2 Na0 plus NB0, right? And the other eigenvalue plus B, this state will be 1 over root 2 Na0 minus NB0. Minus because this eigenvector is 1 minus 1 and 1 over root 2. Okay. So you can now find that this is your correction to the eigenvalues, and this is your final state. After that, it should be the combination of those two states, superposition of. Similarly, this, the second eigenvalues, this is the second correction, so this is the second value, and this will be the eigenvector. So you know how to find eigenvalues and eigenvector. So initially I had this state, both the state was Na0 and NB0, both the state energy eigenvalues was En0 diagrammatically. Now it is, suppose your A is greater than B, then I can write one state go up, so it will be En0 plus A, and this will be okay, is less than, suppose okay, I am assuming that En0 plus B is less than En0. Generally, one state go above, one state go up, below. So N0 plus B. And this state, if the eigenvector is like this, then you will get this state here. And if your eigenvector is like this one, then you will get this state. I think it is clear. Now let us go to the hydrogen atom problem. So hydrogen atom in the weak electric field. And also we assume is uniform, assuming of course weak and along z direction. Okay. So your H prime that we already find for electron charge is negative, so it will be plus E is positive, and say electric field is E0, is E0 Z, then E0, and then you have Z. Okay, so this is your, and if you write this in your spherical polar coordinate, so your H prime will be E0 r cos theta, because spherical polar coordinate z equal to r cos theta. And we are interested to n equal to 2 state. So n equal to 2 state, I have 4 state that I should n equal to 2, L can be 1 and 0, and for L equal to 1, M can be 1, 0, minus 1, and for this M will be 0. So let us denote those state as 2, 0, 0, 2, 0, 0. Let me, order is important for me, so I'll write in a particular order. 2, 0, 0. That means n equal to 2, L equal to, then 2, 1, 0. I want to write in like this. Then 2, 1, 1. Then I'll write 2, 1, minus 1 in this row. And in the column, I'll write 2, 0, 0 and 2, 1, 0, 2, 1, 1 and 2, 1, minus 1. So you have to find this matrix, this 4 cross 4, this 4 cross 4 matrix you have to find. Okay, so you have to do the calculation of 16 elements, but I told you the other day, then you need only one calculation you need, and then you can, for example, suppose these elements are, let us write a ij. Okay, so what will be the a11 element? A11 element will be, first state is side h22, and then h prime h22, right? Because first state is this state has in the row, in the left we have this, in the ket, in the bra, in the ket we have this. Similarly, a12, again it will be 2, 0, 0, and then h prime 2, 1, 0. A13 will be 2, 0, 0, h prime 2, 1, 1, and 14 will be 2, 0, 0, h prime 2, 1, minus 1, right? Similarly, a 2, 1 state. A 2, 1 state means this is first row is completed. Now the second row will be this state. So 2, 1 state will be 2, 1, 0, h prime and 2, 0, 0. Okay. So and so on. So in this way, 16 element you can write. Now this is equivalent to 2, 0, 0. Then we had E0 R cos theta. This is my H prime, and 2, 0, 0. Now we need to know what are these states in hydrogen atom. So that you have to remember, or at least some dependence, R and theta dependence you have to remember. So let me, I think I have, okay, I got this, my note. Okay, so you understand what you have to calculate. All 16 elements you have to calculate, and these are the thing. And these things means, let me write here. These things means you have to psi 200. So in wave function notation, if you write, this is in the bra vector. So star, then E epsilon naught R cos theta, then psi 200, then dqr. And dqr is nothing but r square sine theta d theta d phi dr. Okay, so this integration for the first term you have to calculate. So you need to know what is your bra 200 state, means psi 200 state, and then you have to do this integration. Don't forget this. Some people write dr d theta d phi. That is wrong. R square sine theta of course will be there, because spherical volume is r square sine theta. And integration r should be, r integration should be 0 to infinity radius. Theta integration you all know 0 to pi, and phi integration you know, 2 pi. Clear? Is everything fine?
Yes, sir.
Any doubt you should tell me, because this example is famous and everybody teach this example, because this example has lot of features that will see.
So in calculation,
Huh.
so we cannot proceed as we proceed in the case of harmonic oscillator using the parity.
Yeah, of course. I have not done any calculation. We will not do the calculation. Only one calculation you have to do. All in cases, I'll show that all the elements. So 14 elements are zero, straightforward. 16 elements, 14 elements are zero. 2 elements are non-zero.
Okay, so because in hydrogen atom we have definite parity, so we can calculate like that.
Yeah, we'll use parity. So do you know what is the parity transformation in spherical polar coordinate? Can you tell me?
No, sir.
Okay, so that you should know first, na? Parity in spherical polar coordinate. Okay, so let us what he was suggesting, that we have to use symmetry argument. We will not do the integration blindly. We have to use those things. So parity in spherical polar coordinate. So parity means x going to minus x, y going to minus y, and z going to minus z. Now, this is the standard reflection about origin. This is parity transformation. Okay. So but it is now spherical polar coordinate. So r is your basically x square plus y square plus z square square root. So spherical polar coordinate parity will be r going to r, x going to minus x, y going to minus y. This will not change. So r going to r parity. Similarly, x going to minus x, y going to, if you write your theta going to pi minus theta and phi going to pi plus phi. So this is the parity. You verify yourself. If you make this, write your x, y, z in terms of spherical polar coordinates, you put this, you will get this x going to minus x, y going to minus z. Okay. So this is parity in spherical polar coordinate. Okay. Now, remember, hydrogen atom has a definite parity, and psi NLM state, if you write r pi minus theta pi plus phi, this under parity, this will get a minus 1 to the power L. You verify yourself, because psi NLM is nothing but your R RNL R and YLM theta phi. This is the spherical harmonic. So hydrogen atom wave function, you need to know spherical harmonics, and this is radial part. So you should familiar with this wave function, and under parity it's just minus 1 to the power L. That you verify yourself by putting this transformation in as a parity transformation. So now just quickly, what will be this psi 200 star E0 R cos theta psi 200, then there is a cos theta sin theta dr r square sin theta dr d theta d phi. So this integration, so this has L equal to 0, so this parity is even. This term has also parity even. Okay. Sin pi minus theta is also plus, so this also even. So this has plus parity, this has plus parity, this has plus parity. and this has cos pi minus theta is minus. So whole term you have a odd inner parity. Okay, so odd under parity. So this integration will be 0. Now you verify yourself. You have to do this integration. See, I just write theta dependent, cos theta, then sin theta, d theta. This is the only term, 0 to pi. If you integrate, you will get 0 directly. But from parity argument, I am saying this. Now if I have any term, any diagonal terms. So diagonal terms, so this is the first A11 term is 0. That from parity argument. Also, you can directly verify. For the first time, you should verify directly. Now, if I write psi 210 star E0 r cos theta psi 210, then sin theta d theta. We don't need to go to other. What is the parity of this term? Anybody? Plus or minus?
So plus.
Minus.
No, it is minus 1 to the power L. I said L is 1 here. So it is minus parity. This also is a minus parity. This has a minus parity. But this sin theta, of course, has a plus parity because sin pi minus theta is sin theta. So total parity again odd. So again this integration. So this is actually your 2 a 2 term is also will be 0. Similarly, A22, A33 term will be psi star 211, then again cos theta psi 211, and then sin theta d theta. I'm not writing R integrations, just theta integration. So this is also, this is odd, this is odd, this is odd. 3 odd, so minus, this is even. So again, this is 0. And similarly, A44. So 4 of the elements in this matrix we found. So it is 0 here, 0 here, 0 here, 0 here. Okay. Do you have a class after this? Hello.
No, sir.
No, sir.
Okay. Okay. 5 minutes I'll take. No, not more than that. And then similarly. Now I know that 16 elements, 4 of them I have found all are 0 from my argument. Now these two will be non-zero. That I'm saying you will calculate, and this will be just same term. Okay, because as I told you, this if the operator is Hermitian, this term and this term is Hermitian conjugate to each other. So now what about this term where m is involved? M means this term. Suppose psi 200 and er cos theta and psi 211 or psi 21 minus 1. Okay, these terms now I'll consider. Now this term you cannot say 0 with parity. This term, because this has a this is even parity, this has odd parity, this has even parity, this is odd parity, this is odd, sin theta is even. So this is total is even parity. So parity argument will fail here. But it is very easy to see the phi integration here. Phi integration will be, so psi 11, just a moment. Hello. Is 0. So this, unless m equal to 0, all term is 0. So I found that whenever m equal to 0, not only that, here these terms also will be 0 because there is m. Here there will be m, so this term will be 0. So all terms are 0 except these two terms. Here m is 0, so it cannot be 0 from phi integration. Here parity is even, it cannot be 0 from parity argument. So this integration will calculate in next class. Okay, so I'll stop here. So this integration, to calculate that, you should know what is your psi200 function, psi210, and psi yeah, two what are the terms? Psi, this integration means, okay, and psi00, psi200. These two wave function you should know, and I can write you this two wave function, 1 over 4 root pi, you just 4 root 2 pi, 4 root 2 pi, 1 over a0 to the power 3 by 2, 2 minus r by a0 e to the power r by 2a0. Okay, so this is psi00, psi00 term, and psi210, this term will be 1 over 4 root 2 pi, 1 over a0 3 by 2, r by a0 e to the power minus 2 by no, r by 2a0 and cos theta. So these are the two terms we will need to do this R integration, and R integration will be gamma function integration, and also we'll do the theta integration. So those integration you have to do this. Okay, so please go through argument that 14 element in that 4 cross 4 matrix I have argued to be 0. Please understand that. If you have not understood that, bring this question in the next class. I will do this calculation of psi 200 e r cos theta psi 210, and this result will calculate in next class. And once we calculate, then we'll do the perturbation. So 16 element we have to calculate, but 14 we have calculated today, all are 0. And 2 are equal, so only one element will calculate, and this is that. Because this integration will not be 0 due to parity, it will not be 0 due to m integration. So this will be non-zero. Okay, so I'll stop here unless you have some quick question.
So I have a
Sir,
doubt.
Huh.
So
Tell
in
me.
case of harmonic oscillator, we solve it using the annihilation and creation operator, and that operator is not Hermitian. So it is safe to use them.
Yeah. Hermitian, when you use, if you see, when you see a dagger acting on this state will give you root n plus 1 n plus 1 state. Now if I can make it a Hermitian conjugate, a acting on the brass state will give you my similar things. So a dagger will become a. So you have to consider that. Okay, they are not physical operator, right? Physical operator has to be Hermitian. They are not physical operators.
Oh, okay, sir. And I have one more question. So this operator method, in the case of harmonic oscillator, we can solve it harmonic oscillator potential much more easily than the differential equation method. So why can't we generalize this method to other potential problem like the hydrogen atom and the particle in a box? Why it is limited to only this problem?
Yeah, you try to find for hydrogen atom. No, who is restricting you? Try to find the
So,
operator method for no. Try to find yourself the operator method for hydrogen atom. No problem. But it is not that easy as in the case of simple harmonic oscillator. That is why people use for simple harmonic oscillator, but other potential also people use creation annihilation, and for hydrogen atom it is difficult. You are not able to find, so you have to find a dagger commutator will be 1. All these things properties has to satisfy. So you define your a dagger, and also your Hamiltonian has to be written. First of all, hydrogen atom is 3-dimensional, so you need 3 operators, a1, a2, a3. So it is not easy. If it is easy, people would have been using that. No, we will be using only the easy. Yeah.
focus, so we can generalize that the operator method is a general method, but it is not always applicable.
Yeah, if you can find this method applicable, and for some other potential people use. Not only that, supersymmetric quantum mechanics, if you learn something which is not a student your course, then it will be there are potential where can be used, and there are many places creation annihilations are used. In quantum field theory, creation annihilation will use infinitely many creation annihilation operator. So there are used, but you have to find where it is useful and where it is not useful. For
Okay,
hydrogen
sir.
atom, it is
It is
not.
not practical.
Yeah, yeah,
Not
yeah.
practical. Okay, thank you, sir. Thank you.
Anybody else? I'll stop otherwise.
Sir, how you define YLM? Sir, I don't recognize it.
Yeah, so you go through a hydrogen atom book, quantum mechanics book, and YLM, how the wave function comes in the hydrogen. So you have to study hydrogen atom. That in the differential equation solution, YLM, and also YLM is given in mathematical physics book, right? This is spherical harmonics. So I didn't teach this. So you have to find from your hydrogen atom how this solution comes. Wherever you have angular momentum, these are the eigenfunction of angular momentum. So that you have to find. I didn't teach it here. Okay. Any other? Okay.
Hello. How, sir? Yeah, then our next class is on Saturday, and the Saturday is Saraswati Puja. So kindly it can be changed. Hello.
We'll talk about this in the group.
Okay, sir.
Hello. Hello.